Okay, so thank you. Good morning, good afternoon, everyone who is present here. No, thank you a lot for the professors who agreed to be evaluating this work by Fávero today. We'll start right now with the our first phase of his defense, which will be the presentation of his research work that Fávero has done here at the Federal University of Paraná, which I have advised along with Professor André Mariano. So thank you again for Professor Henrique Hervé, Hamilton Klimak, Sérgio Pichorin e Eduardo Lima, who will evaluate this work. And Fávero, whenever you are ready, you can start your presentation. Thank you very much again, and you can start your presentation.
Okay, thank you. Hello, my name is Fávero Santos, and today I will present my thesis, a single propagation path, multimode CMOS power amplifier based on the stacked topology. I was advised by Professor Bernardo Leite and Professor André Mariano. I would like to thank the evaluation committee and the guests for their presence. So, the transmit power control, or TPC, is a mechanism of modern standards employed to increase overall efficiency of the transmitter. It is employed in high-efficiency wireless communication standards, such as the IEEE 802.11ax. At the physical level, it can be seen as a modulation of output power as function of the application. However, for typical power amplifiers, the decrease of output power causes the decrease of efficiency. What if the reduction of the output power caused the increase of efficiency? One power amplifier topology that allows the increase of efficiency as the output power is decreased is the multimode. Multimode power amplifiers are the power amplifiers that have more than one efficiency profile. Efficiency profile is the curve that describes the efficiency of a power amplifier as a function of the output power. In other words, it is the capacity of such circuit achieving peak efficiency levels for different output powers. A power amplifier that has only one efficiency profile is called a single efficiency profile or a single mode power amplifier. However, when the power amplifier is capable of achieving multiple efficiency profiles, it is called a multimode power amplifier. If the output power is set to a fixed value for the efficiency profiles described in A and in B, the power amplifier in B is capable of achieving higher efficiency as its second efficiency profile achieves peak efficiency levels while power amplifier A does not. Multimode power amplifiers can be designed as a single path and as a multipath architectures. Multipath multimode power amplifiers are circuits that achieve multimode by employing multiple paths for the RF signal. Single-path multimode power amplifiers, however, are circuits that achieve multimode operation with only a single RF signal path. The trade-off between the two architectures is the area and optimization costs. For the second one, the optimization cost is generally lower, but the area is generally higher. For the first one, the area tends to be reduced, but the optimization cost is generally higher. Apart from the architectural aspects of the multimode power amplifier, CMOS power amplifiers, in specific, have to deal with an issue which is intrinsic to this process, low breakdown voltage. The CMOS process has low breakdown voltage, which limits the supply voltage and thus the output power capability of a power amplifier. So how to deal with this issue? How not to limit the output power due to the low breakdown voltage? One way to do so is to employ vertically series connected transistors, a technique called stacking. As will be discussed later, stacking allows each of the series connected transistors to share a high supply voltage and thus to achieve a high output power while still complying with the low breakdown voltage. Based on the modern mechanisms to increase power amplifier efficiency, on the adequacy of the multimode architecture to meet such trend, and on the issues related to CMOS power amplifiers design, it is conjectured that it's possible to achieve multimodal operation in a stacked architecture if somehow its transistors could behave either as amplifiers or as closed switches. That being said, the objective of this work is to test the stated hypothesis by designing, presenting, and discussing the post-layout results of a 130 nanometers CMOS power amplifier. To do so, we will start by reviewing some base concepts that led the discussion to the proposed proof of concept architecture. The cascode configuration, which is presented in Figure C, is typically composed of two vertically connected transistors, the lower one as common source and the upper one as common gate. The reliability requirements in Figure D for the cascode are accumulative in relation to the common source configuration. In this thesis, the Vmax value is used instead of VBR. The main difference between the cascode configuration and the stacked configuration is the presence of signal at the gates of the upper transistors. The main idea behind this topology is the step-by-step, or transistor-by-transistor, voltage amplification. At the output, the amplified voltage is at its maximum. The DC voltage distribution of the circuit may follow the presented equations. In this work, VDS was made equal to Vmax under 2, while VGS can be set as a function of the linear class for amplifiers. Finally, the supply voltage may be defined by the stack height N multiplied by VDS. Based mainly on these types of configurations, it can be found in the literature several examples of structures and techniques to achieve multimode operation. For example, the power cell combination, which is the enablement or disablement of parallel amplifying cells. Or the supply voltage scaling, which is the increase or decrease of supply voltage. The load modulation, which is the selection of predefined optimum output impedances. The architecture selection, which is the selection of predetermined amplifier architectures. And often power amplifiers employ more than one technique to achieve multimode operation. For example, it is in the shown circuit, the architecture selection occurs when V mode is at high or low voltages. When in high, M29 and M30 are in cascode configuration. When V mode is low, M29 and M30 are in stacked configuration. Simultaneously, the supply voltage should also be scaled. Based on the effort to expand on the techniques to achieve multimode operation, this thesis presents the hybrid configuration. In the hybrid configuration, the stack height is equal to the sum of A transistors operating as amplifiers, and S transistors operating as closed switches. When N equals A, the circuit operates as the stacked topology. When N is different from A, the circuit operates as the hybrid topology. Some transistors operate as closed switches and some as amplifiers. When A equals 1, the structure operates as a common source. In this sense, the modes of the hybrid are defined by triplets NN, AA, SS. For example, N3A3S0 with high supply voltage, N3A2S1 with intermediate supply voltage, and N3A1S2 with low supply voltage. The DC voltage allocation of the hybrid follows the same rules of the stacked configuration. However, as modes change, the supply voltage should be scaled. An example of voltage allocation for the hybrid is presented in the table 2.1. In summary, the hybrid employs the stacked topology and adds to it the supply voltage scaling for the selection of the transistor behavior capabilities. The need of optimization of the gate capacitances is intrinsically tied to the transistor behavior selection. How these concepts are tied together and how they concretize a single propagation path multimode power amplifier circuit will be discussed in the following slides. The proposed circuit is composed of an input matching network, a feedback resistor, a capacitor bank, a choke inductor, a power core, and an output matching network. The power core is composed of 4 stacked transistors, each one of them with a width of 1.2 millimeters, a channel length of 240 nanometers, double multiplicity, and 20 fingers. The sizing process of the power core and the gate capacitances were based on a supervised optimization process based on large signal targets. It is supervised because in a plethora of results, it is the designer who decides the trade-offs in the performance of the circuit. It is optimization-based because it uses the optimization algorithms on the design tool. Finally, the optimization targets are related to large signal metrics. This figure exemplifies how this process happens with the cadence flow. In the schematic view, a transistor is placed and the number of fingers, formerly an integer, is altered to NF. In the simulation view, NF is automatically considered as a design parameter, and its range of variation can be altered. It is important to know the limits of each design parameter because there are often design rules that physically limit the circuit. Later, output expressions related to large signal metrics, efficiency as a function of the output power, for example, are defined, and specific targets such as efficiency equals 30% are set. Then, the simulator is set to optimization mode, and simulations are initialized. Finally, the obtained design parameter value is set in the schematic view. This example only discussed the usage of one parameter and one target. In fact, the designer should set as many parameters and targets as possible, and his main focus should be on the trade-offs and on the relations of the parameters and targets of the circuit. The supply voltage is fed through the V-power pin. The supply voltage for the circuit varies from 2 volts to 3.8 volts. The output matching network, which is a high-pass L network, matches the output impedance to 50 ohms. For the presented circuit, the selected load pull impedance is 37 plus J22 ohms. Apart from supplying a DC voltage to the transistors, the choke inductor also participates on the matching. The four insets show that the selected load pull impedance is an adequate choice for all four modes at 2.4 GHz. The efficiency increases as the radius of the closed curves decreases. The linearity increases clockwise. Although this load pull simulation shows the capacity of such circuit achieving higher linearity values, one should carefully consider which load impedance to select, because some impedances cause one or more transistors in the power core to exceed Vmax. As for the biasing tree, it is fed via 4 pins and they should be set as presented in the table. Observe that the voltages lower than 3.8 volts define transistor as amplifier operation and 4.8 volts define transistor as a closed switch operation. The capacitor bank is composed of capacitors and transistors. To size such transistors, the same optimization process discussed some slides ago was employed, but now with small signal targets. The capacitance of such capacitor bank were also optimized for the best operation scenario. To set the adequate capacitor combination to each selected mode, enable pins are employed. The configuration for each mode is presented in the table. The feedback resistor is employed to increase the circuit stability by decreasing the circuit's gain. The influence of such resistance on the stability is non-identical to each mode. Finally, the input matching network follows a high-pass T network topology and is employed to match 50 ohms to the input impedance of the amplifier. Although the presented circuit has 4 modes, the variation of input impedance as modes change is low. The standard deviation of the input impedance for all modes is lower than 2 ohms in magnitude. This slide presents a summary of the setup for the proposed circuit. In detail, the lowest power mode available is the CS, while the highest is presented as HP. In the proposed circuit, changing modes necessarily means changing the biasing tree voltage, the enable pins voltage, and the supply voltage. Regarding the layout, the circuit measures 0.4 squared millimeters without pads. It was laid out with 130 nanometers RF CMOS process from GF. Unfortunately, as our funding for chip fabrication and measurement was ceased, we could not proceed with the manufacturing preparation steps. Nevertheless, we decided to lay out the circuit as clear as possible, hoping that this work would allow other designers to test this architecture by themselves. The inset A depicts the output matching network and the choke inductor. The inductor cells for the circuit are the planar spiral inductors, which are adequate for RF designs as they have the lowest parasitic capacitance. As for the capacitors, the employed cells were the single mean capacitor option. They achieve the needed capacitance for all capacitors in the circuit and have low capacitance dependence with temperature. The inset B depicts the power core and the feedback resistor. The selected cell for the resistor is an option that has low parasitic capacitance, the highest sheet resistance, and the lowest resistance variation with temperature among available resistor cells. As for the transistors, they are thick oxide and FETs with controlled geometry. The controlled geometry allows accurate electrical simulations. In the inset C is presented the capacitor bank, which employs single min capacitors and also thick oxide and FET transistors. Finally, in the inset D presents the input matching network, which also employs spiral inductors and single min capacitors. After DRC and LVS, the RC parasitics were extracted. The following obtained results are from the post-layout parasitic extracted and revised circuit. This figure presents the gain for all modes as function of the output power at 2.4 GHz. The power amplifier's gain varies from 5.6 dB to 8.8 dB. Additionally, it is shown in the figure the 1 dB output referred compression point for all modes. They vary from 15.1 dBm to 19.9 dBm. In this figure is presented the efficiency profiles for all modes at 2.4 GHz. As presented in this figure, modes N4 S0 A4, N4 S1 A3, and N4 S2 A2 present proper multimode operation. Mode N4 S3 A1 is shadowed by mode N4 S2 A2 and thus not employed. The efficiency at OCP1 dB for the proposed circuit varies from 20.5% to 28.9%, while the overall peak efficiency is 29.5%. This figure exemplifies the importance of the optimization of the gate capacitances. The green and dark blue curves are the mode N4 S0 A4, but with only the supply voltage being scaled down. Their performance is below the performance of the N4 S1 A3, which has scaled down voltage and adequate gate capacitances. This shows that scaling the supply voltage is not enough to achieve an efficient 16 QAM signal. The circuit achieves a minimum output power of 14.6 dBm, while still complying with the EVM requirements of the selected standard. The selected works for the comparison to the state-of-the-art are the 2.4 GHz CMOS power amplifiers between 65 nanometers and 180 nanometers, and supply voltages varying from 1 volt to 4 volts. In terms of areas, the proposed circuit, which has no pads, is 4 times smaller than the smallest power amplifier. Before we move on with the comparison, it should be noted that some of these comparisons are being made with simulated and measured circuits. Simulation performance may significantly differ from measured performance. In overall, the circuit has the third highest minimum and maximum linearity, the highest minimum efficiency at OCP1 dB, and the second highest maximum efficiency at OCP1 dB. In terms of saturated output power, it performs the second highest minimum and the third highest maximum. As for efficiency at saturated output power, it performs the second highest minimum and the third highest maximum. With all this information being shared, I would like now to move to the conclusions. This work aimed to test the hypothesis that the stacked topology is capable of achieving multimode operation. It revisited the cascode and the stacked topologies to present the hybrid configuration. In summary, the hybrid is the stacked topology with supply voltage scaling and the selection of the transistor behavior. To verify the hypothesis, a proof of concept operating at 2.4 GHz was designed with 130 nanometers CMOS technology. The post-layout large and small signal, continuous wave and modulated source results were presented. By comparing this work to the selected state-of-the-art, it was possible to observe that the proposed circuit has compatible performance and also occupies a small area. However, there is room for improvement, such as the improving of the layout, placing pads, increasing the amount of stacked transistors, and adding a gain stage. Additionally, during these doctorate studies, these works were developed. Finally, as for the suggested future works, it is possible to use this architecture in multi-band, multimode power amplifiers, using the hybrid as the unitary cell for multipath, multimode power amplifiers, and using it in an envelope tracking power amplifiers. With those final remarks, I would like to thank the evaluation committee for the time and effort on reviewing my work and for participating in this presentation. I hope you all had a wonderful time and that this idea may somehow affect positively on your work. Thank you.
Thank you, Fávero, for your presentation. We will now move to the second phase of your defense, which will be now consist on the questions and considerations from the professors in the committee. We'll start by Professor Henrique Hervé from Bordeaux INP, who is participating with us from France. Henrique, it's a pleasure that you have accepted to evaluate this work. And please feel free to use as much time as you need to share your comments and ask any questions to our candidate, Fávero Santos. Thank you again, Henrique.
Okay, thank you, Bernardo. So I would like to first thank Professor Bernardo Leite and also Professor André Mariano for this kind invitation to be a member of this PhD thesis jury. Some general remarks or comments about the presentation. I appreciate the quality of the presentation. For me, this presentation is clear and precise and with a good level, scientific level. I think that the candidate has demonstrated his scientific skills in the design of CMOS RF power amplifier with an innovative approach with the hybrid structure. And the PLS results are quite convincing, and I think that these results validate the PA design approach, and we can see also that there is a good production about in terms of papers. So now I have some, maybe a lot of questions. I will start with the application. I see that you target an application at 2.4 gigahertz, and I would like to know why you choose this application.
Yeah, sure. Thank you for your comments, Professor Henrique. We chose this frequency of operation because it is simultaneously employed in Bluetooth communications and in the IEEE 800 and 211AX wireless communication standards. So we thought it would be a good matching between application of the circuit and development of the theory.
Okay, okay. I have a question about the amplifier on the operating class. How do you choose this operating class targeting the 2.4 gigahertz application?
So in this power amplifier in specific, we aimed to obtain the highest linearity possible. So we went straight to the Class A power amplifier. So that was the why we chose Class A.
Class A or Class C? Class A, right?
Yeah, Class A. Yes.
A, okay, okay. I have a question about the choice of the technology because you only present PLS results, and I see that the technology is .13 micrometer CMOS from Global Foundries, but if you only present PLS result, you can choose another maybe more perform technology. You know, I think about, for example, SOI or CMOS SOI 28 nanometer or 65 nanometer. So please, could you explain how you choose this this technology for your application?
Yeah, sure. Actually, Professor, we had an idea of using ST technology when we first started developing this thesis. But if I remember well, the problem that we faced back then was that the issue that we faced back then is that we didn't have access to the controlled radio frequency CMOS transistors. So that was the main issue, that we could not use a more advanced type of technology.
Oh, yeah, okay.
Also back then, if you allow me to add some comments on that, also back then, we had the hope that we could somehow fabricate the circuit, because back then our funding was still available. It was only 2 or 3 years ago that our funding was seized. And finally, one thing that is interesting to comment in here is that this technology is following technology of the technology that I employed in my master's. So I was kind of used with this technology. So those are the three aspects on why we decided to use 130.
Okay, understood. I have a question about the hybrid configuration, because we see that some transistors are working as or like switches. Okay, but when you move from one mode to another mode, the output impedance, the optimum input impedance for each configuration mode will change. And I see that you have only a very few change of the output impedance. I see less than one ohm. How do you explain that? Because when some transistors switch from on to off, you choose not only with 1 ohm, but with a so could you explain that? Because I understand that there is another work with Modesto, and where we can see that he need to add a low pass P matching network, reconfigurable matching network, in order to present for each mode the optimum impedance for the transistor. So could you explain that, please?
Yes, Professor. And this is something that I struggled a little bit to explain, but this is a really interesting question. And I guess that's the beauty of the circuit. The gate capacitances in the topology, even in the stacked or in the hybrid topology, they are employed as voltage, AC voltage dividers, okay?
Mhm.
But when you set the gate capacitance, what you're actually doing is matching the output impedance of M1
Mhm.
to the input impedance of M2. So when actually we are changing the gate capacitances, what we are really doing in reality is also doing some kind of load modulation, and
Oh yeah, okay.
and that's why we actually are able to maintain the efficiency high and also the linearity high. But
Yeah.
as I showed, like in this, let me get again this slide in here.
Mhm.
Sorry. In here, as you can see, this is the green curve in here is the highest power mode available, but with non-optimized gate capacitances. And in here is the N3 S3 S1A3, which is the following mode in regards to the amount of modes of the power amplifier, but with the gate capacitances set accordingly.
Mhm. Okay. Okay, I have a question about the bank of capacitors. How do you drive this different? Yeah, here we can see. So you have the gate capacitance, and how do you drive that? You have a digital rod to drive that or not? How do you do that?
Okay, so if I understand well, we drive the circuit by applying high or low voltages at the enable pins in here, LPN, NPN, and HPN. By doing so, some switches are in on state and some switches are on the off state.
Yeah, okay. But the value of the different gate capacitors, you have different value?
Yes. Okay, sorry. So these gate capacitors in here, they
Yeah.
were all optimized. What I had to do was to optimize each one of them regarding to the mode of operation of the transistor. Actually,
Yes.
sorry.
No. After the design, it's not possible to change the value of each gate capacitance.
Yes, it is possible.
It is possible,
Actually,
okay.
this is the revised values of the gate capacitances. Those are not the schematic values. What I'm presenting here is the updated values that I obtained after post layout extraction.
But after the fabrication of the circuit, it's not possible to change the value of the capacitance, right? After the fabrication.
No, this is a fixed setup of capacitance.
Okay.
Yes, but you said something interesting. Maybe if instead of a ground pin in here, we added a floating pin in here, maybe externally we could add an external capacitance, so the fabricated circuit could have different gate capacitances from the predefined values.
Yeah, and maybe you can add also some varactor to change. Because there is no problem of linearity with this capacitance.
No.
Okay.
Great.
Okay. I have another question about I think slide 52 about the feedback resistor.
Yeah.
I think that something is missing because we see the feedback resistor between the drain and the gate. But you need also a capacitance in series with the resistor, no? Because if you forget the capacitance, you will have a problem of bias between the drain bias and the gate bias.
Let me check if I remember what I did in here. Yes, I understand what you just said. Yes.
Because in this case, you will have the drain bias of the, I think the M3 transistor will impact the gate bias of the M0 transistor.
Yeah, I understand what you're saying, Professor, but something that happens in the circuit is that VB1 is always fixed in 0.52 volts. So we'll actually have the drop between the drain and the gate of M3 and M1, but as the circuit always have the same fixed VB1, I designed the circuit to walk around the situation. So maybe it would be a better idea to add the C1 so I could not face this type of issue. Yeah.
Could you explain exactly the function of this resistor?
So yeah.
Why? Yeah, please.
So I employed this resistor to increase the stability, the mu stability, the output mu stability of the circuit. What I observed during small signal simulations when I swapped frequency, I observed that some modes of the power amplifier, especially like the low power modes, were unstable. So I tried some topologies like only the resistor and the resistor in series with the capacitor, and also an RC bank. And the best configuration that I found was only the resistors. When I was watching the variation of the stability for all modes and the obtained performance for all modes. So
yeah.
So when I say that the influence is non-identical to each mode, is that I have to do lots of simulations in here to find the best value that would make the lower output power amplifiers.
Because I think that also this resistor will degrade the gain of your structure, no?
Yeah, it will. You are absolutely right. Yes, it does degrade the gain of the structure, and that's why the gain of the structure is below 10 dB, if I remember correctly. Yes.
Oh, okay. I have another question about the choice of the transistors, because I know that with the foundry you have different kind of transistor. I think about LVT or RVT. So how do you choose the transistor for the structure?
Yeah. So in this process, Professor, we only have if I may say that RVT transistors. Okay, there is no LVT or any other kind of options in this process. Okay. So what I had to actually choose from was the NFET, the NFET or the NFET RF, or the double gate, which is the thick oxide transistor, and the thick oxide transistor and the RF thick oxide transistor. So between all those four options, I choose the thick oxide transistor with controlled geometry, which is the suffix RF. Firstly, because I could achieve higher output power because the breakdown voltage, the Vmax voltage of the double gate transistor is higher than the regular transistor's Vmax.
I have a question about the matching network. I see that you have LC configuration for each of them. But we know that a very popular configuration is based on transformers, and we know also that the size of the transformer is quite similar to the size of a self-inductance. So, could you explain also how you choose the configuration of your matching networks?
Yeah, sure. So, for the matching network, I strive to find the simplest form of matching, which I understand as the passive networks. I also had the opportunity to work with a doctorate studies candidate in which we discussed a little about using transformers in this type of topology. Unfortunately, this branch of this work didn't went further. So to not rely on the work of other students, I decided to use the simpler version of matching networks. So it was actually, if I may say that, it was actually a practical decision. Yes. But
Okay.
yeah, I understand that matching with transformers is you will get lower losses, and the size would be similar. Yeah.
Okay. And a final question is about, I see that your PA has a narrowband behavior, right?
Yeah.
Narrowband.
Yeah.
It's not a wideband. So, but okay, we can see here. Yeah. Okay. Can we improve the bandwidth with this kind of hybrid architecture or not?
Yeah. Yes, Professor. I believe we could improve the bandwidth of this architecture. When I was designing the power amplifier, I actually tried some wideband matching networks at the input and the output to observe if we could somehow achieve wider operation or wideband operation. So I believe if we change the input matching with some other type of circuit, and also change the output matching with some other type of circuit that allows wideband operation, I understand that it would be possible. Yes.
So okay, so I have finished. Thank you for the presentation. Thank you also for the answer to the question, and I would like to congratulate you for this very interesting work. So thank you, Bernardo.
Thank you so much, Professor.
You're welcome.
Thank you very much, Professor Henrique Hervé. Now we will move to our next member here of the evaluation committee. We'll go now to the questions and comments from Hamilton Klimak from the Federal University of Rio Grande do Sul. Hamilton, thank you again very much for accepting to be here in this PhD defense. Please take the time you need to address your question. Thank you.
Okay, thank you. Thank you, Fávero. Thank you, Bernardo, for inviting me for this jury. I will divide my comments in the relevance of the topic. I think it's high. Wireless communication is the big bottleneck for mobile and autonomous networks today, and optimizing power amplifiers is very important. The structure of the text, I think the text is too compact, and sometimes it's hard to follow the idea. In some points I had to go forward and back again and forward again. So I think you could improve a bit, Fávero. I think it seems like a paper. Do you understand? When you write a paper, you have space limitations, so you have to be very straightforward when you put your ideas. This is not a paper, this is an academic work. I think it will be a good work to other guys, other students that will want to understand about power amplifiers, RF systems, and so on. So I think you could improve the generic, for example, the introduction is very short. You could give a better idea about the RF scenario, the perspectives, the needs for power amplifiers optimization. So you can give a context for your work to justify your work. it's important to give to the reader. I always say to my to the students that I advise that you have to use the introduction to give a strong idea for the reader that why you are doing this. So I think you could improve some parts of your text, like the introduction, for example. I did a document with some suggestions pointed out, so I will send it to you, and then you discuss with your advisors about what you should or not include, and so on.
Thanks.
And now I am giving only a generical suggestion.
Thank you.
And again, in the theoretical foundation, I think you could, for example, do some small signal analysis of your circuit to justify the use of the stacked configuration instead of the cascade, for example. The stacked configuration is based or depends on the CGS capacitance, for example. The element that sends signal from source to gate is the parasitic capacitance, but it's not mentioned. It doesn't appear in any figure. Do you understand? So a guy that doesn't understand the details behind stacked configuration will not understand how the signal goes from source to gate. And you can find in any figure this capacitance.
I understand what you're saying, Professor. Yes.
Yes, I think you could explain better how this configuration works, doing small signal modeling, doing some analytical derivations to show how the signal goes from the input to output, how you can estimate gain, input and output impedance, and so on. I think you can improve this part of your text, and it will be a better tool for new students to study this topic. Okay.
Yes. Okay. Thank you, Professor. I understand what you're saying, and I understand the importance of CGS. So I guess it should be something that really should be added to the thesis. Yes, I understand and I agree.
Okay. And one question about the fundamentals. Why is it necessary to disconnect the capacitor C1, C2, and so on when you put the transistor to the triode to the
voltage at the gate from the previous drain. So it is employed to first maintain the transistor, the Vmax voltage in the transistors, the breakdown voltages of the transistors under control. And actually, when I was preparing the circuit, I observed that not necessarily the capacitances for each mode are similar or could be employed he employed once again when mode changes. So I thought it would be an easier way to show that the correct gate capacitance should be set. So as I'm showing this figure in here, there is no really connection between sorry, let me rephrase that. I didn't find I don't know, and I didn't find it, if there is a connection between modes and a specific value of gate capacitances. So what I did was actually explode this power amplifier in 4 different power amplifiers. In each power amplifier, I optimized gate capacitances, and then I had to rework the circuit in order to make the gate capacitances adequate for each mode, and try to make those capacitances not interfere with the other modes of operation of the power amplifier.
Okay, but I think you could explain better in the text about this.
Okay.
Okay. Isn't possible to have an analytical model that could allow the calculation of a first guess? If I understand correctly, your approach is always based on simulations to size the devices, the transistors and capacitors, yes, and so on. Isn't possible to have any analytical model that you could at least have a first guess of the transistor sizing, for example, before to go to the simulations? Did you try to find it?
Yes. Yes, not only for the transistors, Professor, but also for these gate capacitances. In the writing document, there is an equation that some works employ to determine the gate capacitance values. So, but they use a small signal model in a really low frequency operation. So using those values does not necessarily reflect the reality of the operation of the power amplifier at 2.4 gigahertz, where the transistors are really capacitive. So they are really good starting points for the capacitors, and they can be employed for starting points. But when we are talking about large signal, I understand that the best thing to do is to rely on the models that the manufacturer and rely on the design tool to help the designer with the appropriate values. As for the transistor, it's the same issue. There are some fundamental equations that we can use to size the transistors, right? But again, it does not contain all the elements and all the effects that the full model has.
Yes, so, I see, but they could give you a first guess, so you can start, always when you start an iterative simulation, you can start from one point.
Yeah, I understand what you're saying, Professor, yes. I based this circuit on my experience, to be really honest with you, because I had my experience on the masters on doing that, on selecting the sizing of power transistors. So I had a previous knowledge on which size would be actually adequate for a starting point. So
but your experience is not inside your text, do you understand?
Okay, I agree completely with you, Professor.
So I think perhaps you can give to the reader a starting point to understand how you can size everything in this design.
Okay, Professor, I understand. Thank you.
Also about the inductors you are using in your layout. I suppose you did not use any electromagnetic any electromagnetic simulation for these inductors. I suppose you are using the lumped models, the foundry send with the PDK, yes?
Yes, Professor. I'm using the standard cells of the PDK, yes.
And did you think about to use any kind of electromagnetic simulation to check the behavior of the layouted inductors? No.
So I briefly thought about that, but I didn't do any work related to that. I had a colleague, a doctorate colleague that is working with inductors and simulations with inductors, and we had a brief conversation, and we trying to do something together. As I explained to Professor Eric. But unfortunately, this partnership didn't move on forward. So I had to follow the most straightforward path, which was using the standard inductor cells, and not going further on checking the validity or the modules of or the values, obtained values or quality factor or anything like that with electromagnetic
Yes.
simulations.
I don't worry exactly about the lumped models, but I see two inductors. The left two inductors, the output inductors, they are very near. Is it possible to have any electromagnetic coupling between them?
Yes.
The lumped models doesn't. The lumped models suppose you have an inductor and nothing around it.
Yeah, I understand what you're saying, Professor. And yes, I guess you're correct. Maybe there's some kind of coupling, and maybe the inductances they change due to that. Yes.
And
well,
perhaps
just to add another comment on that, the spiral inductors, they have a low metal grade that actually shields the inductor, but I don't think it will be enough due to maybe the proximity. I would have to check that.
The shielding for inductors that are provided by some processes is only for capacitive coupling, not for inductive coupling.
Oh, okay.
Do you understand? If you shield the inductive coupling, you shield your inductor. You don't have inductor.
Okay. Okay.
So it's only to reduce the capacitive coupling with the substrate.
Oh, okay.
So I don't know if you or the group plan to send it for fabrication or not in the future, but I suggest to check the coupling of these inductors. Perhaps you could move the position and to reduce it.
Okay.
If it is necessary.
Okay, thank you for your advice, Professor.
Also, you thought about any problem related to parasitic inductances of the tracks and so on. It's not extracted by post-layout extraction. No, and you are operating very high frequency.
Yeah. I only extracted the resistor and the resistance and the capacitance for the circuit, and I did not extract the inductance. Yes. When I set up the simulator, I had some issues when trying to extract the inductance. So my first approach was to use the RC extracted circuit. I don't know if I don't know, and it's something that I have to check, Professor, how the inductance of the tracks will affect the circuit. I know that the most sensible areas of the circuit are the RF signal propagation path, right? The input matching and output matching, and especially between those two stages, the output is way more sensible to changes in inductance. So yes, it would be a really good idea to also add the extracted inductance to check the variations of the circuit.
In fact, you have a distributed impedance in the tracks and so on, and when you are doing a layout for gigahertz frequencies, and the layout is not so simple, so perhaps you could describe the strategy you were using to compose the layout, to position the devices. It's not a simple task to decide where and how you distribute the device over the area for high frequency. I think you could explore it more in your test, in your text.
Yes. Okay.
Okay. And again, I think Professor Eric already asked you about that, but I am not satisfied with your answer about the feedback resistor. There are one resistor. You said you were using it to improve the stabilization of your circuit. Yes.
Yes, the stability, the mu output stability of the circuit. Yes, the small signal stability. Yes.
But against what? When you think about to stabilize anything, you think about to stabilize against anything that is taking it out of the point of operation, or any parameter is sensible to.
So yes, actually, Professor, what I observed is that when you vary the frequency of operation of the circuit, you'll see that some regions of operation frequency are below the stability point. So in some frequencies,
just a point. Stability point, you mean related to oscillations, to another?
Yes. Yes. So what I use in here is the mu stability factor, which is a factor that describes the stability, the overall stability of the circuit. And when I was checking the frequencies that the circuit is stable and unstable, I observed some frequencies, some bandwidths that the circuit is not stable. So this resistor, it is employed to increase the efficiency of the power amplifier at some frequencies. So in specific for the mu stability factor, the stability factor should always be higher than 1, just to give you a numerical sense of what I'm trying to explain here. And in some regions of the varied frequency, when I varied the frequency of simulation, I observed that under some frequencies, the signal, the mu factor was well below 1.
Did you try to find other ways to improve the dynamic stability of your circuit instead of using negative feedback?
No, the negative feedback was the only option that I used to increase the stability of the circuit. I tried other configurations, but the resistor only was enough for the circuit.
Because in my opinion, you are killing the gain with this feedback. So sure, you will improve the dynamic stability because you are killing the gain. I don't think I am not sure that there are other ways, but I don't think this is the optimal way to improve stability.
Well,
so you design an amplifier to have gain, and you have a problem. You have dynamic instability, so you kill the gain.
Yeah, but I understand what you're saying, Professor. But this was designed to be only the power core of the power amplifier, and in some power amplifiers you actually have 2 stages: the gain stage and then the power stage. As we're talking about a power amplifier, I know that the gain is relatively low, but I'm more concerned about linearity and efficiency of the power amplifier.
Okay, I understand your point.
Yeah.
You can improve gain in the previous stage.
Another thing, Professor, is that when I was doing some consultations on the selected on the state of art, actually using the resistors to improve stability, or resistors and capacitors, or something like that, or RC banks or things like that, is not a really strange technique in power amplifiers.
Did you think about to use any switched resistor to change the feedback from mode to mode and so on?
That's a great question. I did, but I thought it would be easier. Actually, it's harder to have an only value that optimizes the stability for out circuit, but I didn't want to add another set of switches, and another set of control pins and things like that. I try to maintain myself, I try to maintain the power amplifier operation as simple as possible, only changing what is really needed. So that's why I didn't add a variable resistance, but you are correct. And actually, sometimes the R1 value, it degrades way too much the gain of some modes and not way too much the gain of other modes. So it was a really, as I can say, intense trade back when selecting the R1 value.
About the curve, the result, the simulated curves. If you see the gain curves, you check that the high gain curves are very near, probably because of the feedback. The feedback tends to stabilize the gain. You have a fixed resistor giving you a fixed feedback. So you change the main core gain, but the resistor tends to keep the gain
under control.
Ideally the same. The only curve the gain is lower, the black one, I suppose, in this figure, probably is because the loop gain is lower and the gain falls. When you switch, the feedback is not very functional for this low gain. Probably, I don't know, but maybe if you use different feedbacks for different modes, you could have a better spread of your gain modes in your charts.
Yes, Professor, I agree with you, and I share your feeling. Yes,
but again, you should discuss this point in your work. Do you see? This is a very important point. How you choose the resistor, how you choose the feedback, the impact of the resistance, the feedback you are using in the gain behavior. Another options, for example, you could discuss about to switch this resistor and finally say, oh, I prefer do not switch using only one resistor because of that. But this is an academic work. You should discuss what you are doing, not only put the results of your. I think you spend hours and hours and hours discussing with your advisor, researching papers and thinking and burning your brain about this point, and nothing of this is in your text.
I understand what you're saying, Professor.
Please understand?
It's
important to people that read. When we do a writing work, like our thesis, this is to other people read. That's my supposition. So you have you should think that other people could learn from your experience. I suppose through these years you learned a lot about this. You discovered new ideas, and so you should let this experience to other people in your written text.
Okay, Professor, thank you for your advice. Yes, I understand.
About the PVT simulations, I thought you have from the same mode and the extremes of the PVT, you have 6 dB, 7 dBs in distance. I think I was seeing about a gain curves that show the extremes. These curves, you have more or less like in the yellow. If you go to the yellow mode, if you see in the extremes of this PVT simulation, I have 6 to 7 dBs in distance, and it means more than 4 times the gain in distance. Isn't it a big problem? You have large variation.
Yeah, I do have a large variation, but this large variation is at minus 55 degrees Celsius. So the carrier mobility is way different from the simulated carrier mobility at 70 degrees Celsius. Also, the supply voltage is 10% higher.
So this is not because of process variation. This is because of temperature.
No, I guess it is both for process variations, the selected corner. What I'm trying to say, I guess it's the combination of the 3 variations that cause it.
That's the point.
Yeah.
So when you see this figure, this image, you cannot identify what is the cause of this variation.
Oh, okay.
You understand?
Yeah.
You took some extremes of PVT only. I suggest you to split this figure in separate figures where you only do process variation, temperature variation, voltage variation, so you can check what is the problem.
Okay.
This spread is because of process, temperature, the combination of both have the same weight or not. Okay. You only will check this if you split this figure and check only one variable each time. Do you understand?
Yes, I understand what you're saying. I actually do have the tabled results of the unitary variations as you're talking about, but what I decided to present is only the extreme scenarios. But I understand what you're saying, and I'll add this information.
Also, if you are sure about what is the problem, you can discuss about this. What could be strategies to reduce the impact of this variable, if this is temperature or if this is process or so on. But you have to be sure about what is the problem.
Yeah.
You understand?
I understand, yes.
Okay. About, I don't know exactly if process variations is a problem for your circuit, but supposing this is a problem, did you think about any trimming? When you have process problems, one strategy to reduce this is trimming. Did you think about any trimming? Perhaps trimming the capacitors? I don't know. It's only a guess. Perhaps trimming the capacitors of the gate, you can improve the stability of the gain for process variations. Maybe, I don't know. You should check this. Okay. But did you think about any kind of trimming?
So when you're talking about trimming, you're saying selecting the adequate value of capacitance or resistance
for example, you designed a C1 of, I don't know, 1 picofarad.
Yeah. Okay.
For the typical conditions, it is the best capacitor that gives you this definite gain to that mode. But when you have process variation, it's inherent from any foundry. Perhaps the gain change, I don't know, 3 dBs. You can think, I could make a trimming in this capacitor to adjust the right or approximate the right value to adjust better the gain against process, not against temperature and so,
Okay.
but process.
Yeah.
Did you think about any trimming?
No, I didn't think about any type of trimming nor the capacitance or anything like that. I actually was worried about the supply voltage biasing with the dependence with temperature. But as I didn't use any type of voltage regulation circuit, and I supplied it directly with the voltage sources, I didn't think about any type of trimming, Professor.
Okay, but if this design, I suppose, can become a practical design to be embedded in any kind of, you should have. You will not have control of any bias voltage like in an academic test setup. You understand? So perhaps you can.
I agree with you.
You should think about this.
Yes, and just I'm sorry if I'm being too intrusive, but when you're talking about trimming, the idea is to I don't know, use a varactor or anything like that. To trim to set the capacitance values, or
it depends on what you are trimming. You can make a kind of DAC with 2 or 3 bits that you change and add parallel capacitors to change the total capacitance and correct the gain. And if you are trimming the capacitors, maybe you can trim transistors, you can trim resistors, you can trim anything. Perhaps not inductor. Inductor is difficult to trim, but resistors, capacitors, transistors, it's usual to trim this device when needed. But you check, first you have to check if process variation is really significant to the variation, to the total variation, to decide if trimming can or not be an interesting improvement.
Thank you for your suggestion. This was something that I didn't know was a practice, and this is something that I will definitely search for.
Okay, and finally, what do you think are the main contributions and novelty of your work? What is the central point of your work? The main, the new idea, the novelty, the thing that we will emphasize. This is the word that defines my work.
So I guess what defines the most interesting aspect of my work, of this work, is the capacity of achieving multimode operation in a stacked topology. So it's not common to find single propagation path multimode power amplifiers in the literature. Actually, the multi-propagation path, which is the architecture that has, for example, parallel amplifying cells which are enabled or disabled, is way too easier to be found in the literature, because enable or disable power cells and then combining them somehow with a combiner or with a power combiner is a natural idea. But doing that, achieving multimode operation in a stacked topology, which is a typical single mode operation topology, is the main novelty that I propose in here.
Okay. So, congratulations for your work. It's very interesting, really. And thank you for giving me the opportunity to criticize you.
Professor, I would like to thank you for your comments. I think you brought some interesting insights on how to improve the circuit behavior, and some interesting techniques that I guess the industry employs. and also the comments on how to improve my reading document. So I'm really thankful, and I appreciate your effort on doing that. Thank you.
Okay, and I would like to thank Bernardo and André for the invitation too. And Bernardo, it's to you.
Me too, Hamilton. I thank you very much for your contributions. I think we have here also many suggestions that will help us have a much better document, a much better thesis later on. Thank you very much for your contribution. My main comments I will do in the end. Now I will go on to the next member here is Professor Sérgio Pichorin from the Technological Federal University of Paraná, here from Curitiba. Thank you also, Pichorin, for accepting to be here evaluating this work today. You can go on and ask your questions and make your remarks. Thank you very much.
Thank you, Bernardo. I also would like to thank to Professor André for this invitation, and I would like to thank to Fávero for this opportunity to understand a little more about the power amplifier and CMOS configurations. Where is Fávero?
I don't know if I'm visible. I'm sharing my screen. Let me check. Oh, I'm here.
Oh, okay. Okay, you can change to the slides. Okay, it's okay. Thank you. Well, I have just a few comments, a few suggestions on more on the final text, your thesis. Then about the technical. Your results. Your results are very interesting. Congratulations. I think you are a doctor. Okay. What I will say is just little details that you can improve your text at the end. Okay. The first question. It's just a comment. Please don't be don't be sad about it. Okay, you are now becoming a doctor. Doctor normally works with projects. Okay, and you have to have your lattice update. And the first thing when I analyze a thesis or a master, I look at the curriculum of the candidate, and your last update was 2018. Yeah. I didn't find any your publications there, yeah. But thanks to your advisor, I can found on the Bernard's lattice. You have 3 publications: Modesto 2019, Campinas 2020, and Marcept 1 in this year. Congratulations! But I think you have to put this in your your lattice, please.
I'm sorry about that, Pichorin.
You have to keep it updated, because you have the opportunity to found in CNPq or something like that. You have to do this correctly.
If that helps somehow, I actually updated my lattice last week
No.
So I actually added some publications and also updated my works and things that I did between 2018 and 2021. But I actually, to be really honest, I did it last week, so I guess it wasn't the version that you observed.
No, thank you. Okay. A little detail. It's about the title of your thesis. I don't like the word PA because CMOS is everyone knows what is CMOS, but PA there is no problem. You write power amplifier.
Okay.
Okay. CMOS power amplifier based on stacked topology. I think you have to discuss with your advisor but it's important to get more clear and the title of your thesis.
Yes, I understand.
One question, what I agree with Professor Hamilton. I think you have to put more discussions. One thing is, all your results are based on simulation. All results. What do you think, what do you feel, or what you expect when you try to get real results?
Okay.
I think please discuss a little more about this. What is the difference, simulation and real, or what variables can contribute or interfere in your results in a real world, please?
Okay, so I know that the measured circuit and the simulated circuit, they differ significantly in results, in the obtained results. So what if the circuit is ever manufactured? What I would expect is the difference in efficiency of the power amplifier. I would also expect the difference in the output power of the power amplifier, and I guess I believe I will also see some difference in the gain of the power amplifier, considering that supply voltages and enables and biasing trees are all fixed values from, I don't know, the test bench or something like that. But those are the main three aspects that I believe would change from the measured circuit. And I believe those 3 points, those 3 characteristics, they would be lower than the obtained results. But how much lower, I'm not quite sure. But I know I believe they would be lower.
Okay. But I think you can write this discuss these things in your thesis.
Okay.
To make more clear, because with the reader to think about your ideas.
Okay.
And your idea. Okay. In the page in the page 51. You have a table. It's not in the slide. It's in your thesis.
Oh, okay.
But you have a table 4.4, and you make a comparison between 6 works. 6. Your and other 5. Do you think this is enough? This comparison, because when I see 3 your work and 2 others are from the same group of your laboratory, and you have just 3 works and the other people, okay, and this I don't remember the word, but one of them is just a conference paper, and the other are the journal. you think this is enough, this comparison? There is another works or
Yeah, I understand what you're saying, Professor. So what I try to do in the comparison of the state of the art, I try to maintain myself. I try to maintain the comparison close to the comparison of the circuit that I am that I proposed in this thesis. It's not. It's how can I say that? Although there's a lot of papers that discuss multimode operation, it's not that common to find the same metrics or the same metrics employed to compare the works. So if you check that table, you'll see that I had to use some differential topologies with and compare them to this work. And I believe it wouldn't be a really fair comparison because they are different topologies. But what I'm trying to do is to maintain the comparison of the work near what I understand are the works that are the nearest of what I'm trying to propose. Absolutely, there are other works and other literature that can be employed, but I try to maintain myself inside those limits of supply voltage and technology and frequency of operation. That are, when you're talking about power amplifiers, you can find amplifiers operating at 900 megahertz and also power amplifiers operating at 40 gigahertz. So I try to maintain the boundaries well defined, and that may be limited the amount of papers to use in the comparison.
Okay, but you think this comparison is enough for your thesis?
I think it's enough to give a general idea because I know that the measure results will be really, I can say really, but I know they will be different from what I expect from the post-layout measurement results. So I try to do an adequate comparison, although I know that there are many other factors that may change or give another set of results for this work if it is manufactured.
Okay, thank you for your comments. Now I have just small things to correct in your thesis. I think 4 suggestions. First, your slide 39, please. 39. Okay. Yes. I think there is a mistake here. When let me. I can't read, but okay.
So
yes.
You're regarding the table, Professor?
Yeah, no. It's the inset A. Okay. Please. Yes. Okay. Here. Transistor M1. It's a switch. M2 is switch. Okay.
It is wrong. Yes.
It's wrong.
M1 should be an amplifier, not a switch. Not
the switch one is open, not closed. I think so.
Yeah. That's it.
Okay, it's just a small detail.
I'll have to repair that. Thank you.
Not in your slide 44, and even in your thesis, it's your figure 3.3. My suggestion: you have space. You're as Professor Hamilton said. You don't have problem of pages. Okay, you can put this flow schematic in a vertical form. I think it's just a suggestion, because the text, the words are very small. It's very difficult to read, and I think it's an important figure of your work. You can put it all on in one page. I think it's just suggestion. Write in a vertical form. It's a fluxogram, okay? It's better to see and to read the information. I also have just a small mistake in the page 35. You said the capacitor CS6. You said in the thesis it's 800 picofarad. I think it's femtofarad. Okay?
Yes, Professor, you are correct. It's 800
yes,
femtofarad.
Here is correct, but in the test and your text is okay.
Thank you.
Okay. Well, I don't spend your time, our time here, but I have a lot of more questions about orthography, use of the hyphen, or formattation. I will send you by email, and please correct or know if you are interesting to do or not. Just the last one, another is small detail. In the page 15, you're presenting the work of Tarui. Tarui, yes, Tarui, I think it is the pronunciation. You said it's 64 modes.
Yes.
64, but in the title, the Tarui said just 6 modes.
If when you, I don't know if you had the opportunity to check that paper, Professor.
No.
But what, if you allow me, I'll explain to you.
Okay.
What the author of that work do is actually combining reconfigurable gain stage with a reconfigurable power stage, and the results that he observed was 64 operation mode, 64 efficiency profiles when he's changing all the gain stage and the power stage. But what he actually does is, what they actually do is to select the best 6 overall efficiency profiles, but it is actually a lot of efficient profiles that they can select from.
He had 64, but used just 6.
He trimmed it, as Professor Kim said, and used only 6.
Okay. But I think you can put a statement and to explain this, because I read 64 and the title just 6, and I have a doubt about if there is something wrong or just a selection. Okay. My comments is just this. Again, congratulations for your degree and your new degree. I hope. And thank you for the invitation for this presentation. Thank you, Bernardo and André, for the invitation. And I returned to you the word.
Thank you so much, Professor Pichorin, for your comments and your suggestions.
Thank you too, Pichorin. We will also take note of all those suggestions in order to make a better thesis document. And we'll move now to the last evaluator here, Professor Eduardo Lima, here from the Federal University of Paraná. Eduardo, now you can have the time you need. You can make all your remarks and ask questions to Fávero. Thank you very much, you two, for accepting to evaluate this work. Lima.
Are you hearing me? Are you hearing me?
Yeah.
Are you here now? Okay. So, thank you, Bernardo and Mariano, for the invitation. Thank you, Fávero, for the presentation. Congratulations for your final presentation.
Thank you.
I'll start with some questions. To start, I'll talk about the optimization. You talk about that have made two kinds of optimizations, one about the large signal targets and the other with the small signal targets. Okay. So my first question is, there was only one optimization using large signal targets, or there were several optimizations?
There are several optimizations, and each of those let me explain that there is one flux of optimization, but inside that flux of optimization there are several, hundreds of simulations to check from. But the optimization flux for the large signal is different from the optimization. No, it's the same thing, but the targets are different. It is employed the same algorithm and the cadence IDE, just the targets of the optimization are changed. And when we are using the optimization for large signal metrics and for small signal metrics, the targets for the small signal metrics are disabled. And when we are doing optimization for small signal metrics, the large signal metrics are disabled.
Okay. In your test, you said about some guidelines about the optimization. So I think it could be more specific, and you should write what was the objective function. Mm-hmm. And for instance, if it was the PIA, one of the objective function, you can also state in your text what was the specific sweep that we make. So I try to the P out, the P in from 0 dBm to 10 dBm. Okay. I think it's important if you could write those things.
Okay, understand.
In your test. Another question, still on the optimization, it makes about the initial guess. So Professor Heb talk about something about that with you, and I think you should write how did you get your initial guess. If you say about experience, I think you can write my experience say that transistor should have an initial length of
okay.
Another point in optimization is that when you make some project, you choose some amount of data to optimize and some amount of data to validate if the results are okay, if you can, if they can be generalized to other inputs not used during the optimization process. For instance, you can take the same curve and you choose to take half of the points to optimize and half the points to the validate. So you put a lot of curves in your results. Let me just ask you about that. All those curves were used in the optimization, or some of those curves are not used in the optimization?
No.
So your objective function is lower. It has lower data.
So the curves that are presented in the written document are from the post-layout simulation flow. So they were not part of the optimization flow. They are the extracted results directly from the circuit. So they were not data employed in any type of previous optimization. So the optimization process, it really helps in the schematic view and how to set up and to define the values. But when you proceed to the layout and then the post and then extract the parasitics, you have to do little tweaks or little changes in some values of the capacitances, for example, or resistance, for example, or inductances, to compensate the parasitics that you now have that you have not had during the schematic view. So when all this is ready, the circuit is done. The post layout optimization is prepared, and then the results that I'm showing, they are not related to any type of optimization, but if I'm able to say that, the measured post layout simulations.
Okay. So I think you should point something about that in your text. What was the part that was used in the optimization? It was which was the data that was used to validate your design. This is more like a curious. It is possible to do an optimization based on the post layout results. Like I say, could you do an optimization in a co-simulation where you have the schematic simulation and you have the post layout?
Oh, that's interesting. I thought about that when I was doing my layout, and the main issue is that every time you change the layout, consequently the parasitics change. I was studying some possibilities to try to extrapolate the RC parasitics in the schematic view, so I could somehow foretell how the capacitance would behave after parasitic extraction. But unfortunately, I could not find any way to do that, because, as I said, every time you change the value in the schematic, you'll necessarily change the cell in your layout. So if let's say that the change in the capacitance is a really significant variance change, the layout size of that cell, of the capacitor cell, will change, and consequently the parasitics extraction will also change, because the parasitic extraction does not only works on the tracks, but also on the placed components on the layout, in the layout. So I would guess there is a way to do that. I don't know exactly how to do that, but I know there is an option to extrapolate parasitics in the schematic view.
Okay, thank you. I'll turn to the point of you talk about the envelope tracking. That could be one application for your work. One point that I'm asking you is you put results in your test, in your presentation, of single mode operations, only single mode operations, and from one curve to the other you change the mode. I'm asking if you have any results for switching from one mode to the other mode and see what's happened in between.
Okay. Yeah. So I don't have those results. I know that a student in our group is actually doing that and testing that, the dynamic behavior when switching between all four modes, Professor, with a modulated source, with a modulated signal.
Okay. So now to some specific points. If you put in slide 16. Okay.
16?
66.
Okay. 66 or just 6?
66.
Okay, sorry.
No worry.
Yeah.
So at the beginning of your test, in your document, in your written document, you said about that there was a case of unusual efficiency curve.
Yes.
In this figure, you have one case. So my suggestion is that you put something like that at the beginning of your presentation and also in your written document, showing an example, a visual example of what would be an unusual.
Okay.
So
Okay.
Help
I remember that there is a section in the motivation, I guess, that it's discussed why multimodes they should have horizontally spaced curves and vertically curves, such as the dark blue and the green. They still characterize multimode operation, but the black curve is not a really good curve because the green curve has a better performance, right?
In the written document, you say something about the disadvantage of single path. You said about come at the cost of a complex optimization of the design. So you're comparing single with multi-path. So my question is, if you design with multi-path, you can be more, you can optimize each mode. So do you agree with me is that there is another advantage of single path, that is a lower efficiency? We cannot have the same efficiency as we are doing a multi-path, because in a multi-path you can optimize each one isolated. Or no?
I understand what you're saying, yes. And you absolutely can do that. You can optimize each power core, let's say, to have a really efficient performance, right? A really good performance, and I agree with you with that. What I'm discussing in here with the optimization cost of single mode power amplifier, single path multimode power amplifiers, is that often the modes they interact as they have to deal. How can I explain that? As they rely on, especially in this case, in the hybrid configuration as I'm presenting, they depend on the configuration, on the modes, and on the circuit itself. It is usually harder to optimize it, because when you're doing a multipath power amplifier, you're actually doing something that is isolated, as you said, from other modes. And then you just combine it with a power combiner. Absolutely, there should be another round of optimization after all other modes are tied together, as per se. But absolutely, there are differences between optimization in each case, and I would say the optimization case in the single path multimode power amplifiers, they are really more restricted. I don't know if that answers your question, Professor.
Okay. Another suggestion is that you have the cascode figures at the beginning of your test, and you say the cascode for 1 and 2 transistors, and you said you can have any transistors. So and when you talk about the stacked configuration, you put 3 transistors. I think it would be interesting for the written document if you could also put a figure with 3 transistors in the cascode configuration.
Okay.
And to clear the differences between the cascode and the stacked, because they have the same number of transistors.
Yeah, I understand what you're saying, Professor. Okay.
A small comment on the test: equations must be part of the test, so you cannot say C figure number. Equation that must appear as a part of the test. So as shown, you put the equation and then you continue the test. So I suggest you could change all these all over the test. I also agree with the other professors that you could elaborate more in your test, so you can use whatever space you want to do your test. But I would congratulate you for your excellent reading. So it was very good English, and also very good English to speak. So congratulations for that.
Thanks.
And that it's so. Congratulations for your fine work, and I return the word to you, Bernardo.
Thank you very much, Eduardo Lima, for all your comments. We will also take note and try to implement as much as we can. I think the contributions were valuable too. Now, I would like to ask Professor André Mariano to make his remarks and thank him for working alongside me, advising this work with Fávero for all these years. Thank you very much, Mariano. Feel free if you want to ask questions or make any comments now.
Thank you, Bernardo. I'm going to say a few words, okay? First of all, I'd like to thank Professor Carvé, Hamilton, Pichorin, and Lima for this outstanding evaluation and discussion. Thank you very much. Also, thank you, Bernardo, for the partnership and the opportunity to participate of this thesis project. It was very good. Thank you very much. Finally, I'd like to congratulate Fávero for his achievements and for this very nice defense. It was a pleasure working with you, Fávero. Congrats.
Thanks.
Thank you again, Bernardo, and I return the word to you. Thank you.
Thank you. Thank you, Mariano. Me too. I want to thank all the professors here for all the suggestions, the discussions they raised. They just gave us many ideas on how to improve, and right now the thesis document for Fávero, but also it always opens perspectives and ideas for future work where we can expand on what Fávero has presented here. I think it was very interesting for us, and I thank you all of you for your time and your suggestions here participating. I'll try to address just some comments address some important points that you have raised. So I think the main question is the fact, the important fact that here we arrive at the PhD defense without a measured result, without a fabricated integrated circuit. It's especially frustrating in a way because in his master, Fávero, for 5 years ago, he had measurement results on a PA he designed, and we could measure. I think thanks also to Henrique Hervé, who allowed us to use the state-of-the-art test bench they have there in Bordeaux. So we could have those measured results at his masters and not his at the PhD. But even with this limitation, Fávero was able to make an relevant work here for the PhD. Also, so we didn't have these fabricated circuits in the end, but in the beginning we hoped to. So we started working in a technology which was the one that we had available with Moses for a certain number of square millimeters to fabricate. The choice at the beginning of this work on the technology was due to this perspective on fabricating the circuit. Later, they discontinued this program. We tried some other options that didn't pan out, like mine ASIC for example, and but we continued with the same technology for this reason. As Fávero discussed, we contemplated using a 28 nanometer technology. We had the design kit installed from ST. He was right at the beginning. The first version we had installed didn't have all the RF components. Then we had a new version. We could have that, but then the problem was that all the design kit, all the design rules checked. The DRC was only compatible with the root file was only compatible with Mentor Graphics Caliber software, which we didn't have. We only had the verification by cadence, even though LVS, for example, from the same technology worked well with cadence. So if we could not do all this verification, we could not measure, at least we wanted to have something verified in terms of the design rules to present here. We stayed with the same technology, but I think with all these limitations, including another limitation that's very important, that Fávero works full time at the industry at the same time that he was developing this work, and even though with this limited time window he had to dedicate himself to his PhD research, he was able to do significant work here. Of course, with all his capabilities, he had more time to dedicate to this project. He would have gone further, but I think he has gone far enough and has done a job with good quality for a PhD work. So I want to thank Fávero for his hard work along all these years, for more than 6 years since he did his master, all his ideas, his initiatives, the fact that even with such a limited time, he was also an important reference within our group. He was always able to help our master and the graduate students who could go look for him for some more experience with designing power amplifier with the simulation tool, and he has done a very important work with that. So I want to thank you, Fávero, for all your work along with this year, and I will not discuss very much in detail the other technical comments here, but I think we have some very important suggestions on how we will be able to move forward after this work. So I thank again Fávero, thank again Mariano, who has been working with me all these years, and all the other professors who brought their suggestions today. Professor Henrique Hervé, it's very important for me. This is the first PhD defense here, as I am the main advisor defined here, who was my advisor. I am very happy that you accepted to be here today, and also Hamilton Pichorin Lima, who brought very useful ideas for us to conclude this PhD work. With this, I conclude my remarks. Now I will invite all the members for a deliberation room. In a few seconds, you should be automatically transferred to this other room, and I'll leave here. So Fávero will be waiting here until we make a decision on your PhD. So I just ask you to wait a few minutes, and we will be there.
Okay, thank you.
Fávero, para você não ficar no silêncio absoluto aqui, A banca está se movimentando, então, para deliberação, tá? E eu, como co-orientador, não faço parte da banca, vou te fazer companhia aqui. Comutei aqui para o português, porque você tem alguns convidados assistindo no YouTube a sua apresentação, você tem 15 convidados lá apresentando. Gostaria, então, de convidar aos convidados, né, que se manifestem no chat do YouTube para o Fávero poder ver que vocês estão aí. Se quiserem fazer algum comentário, alguma coisa para o Fávero aí, uma pergunta, fiquem à vontade, tá? Eu leio para o Fávero aqui, não tem problema. Ou o Fávero mesmo pode acessar o YouTube, né? Então fiquem à vontade para se comunicar. Você ainda tem 15 pessoas lá, Fávero. O pessoal é fiel a você e está esperando até o final.
São as 15 pessoas que passaram a apresentação e também os comentários da banca, então, nossa.
Legal,
já começou às 9, né?
Sim, começamos às 9, mas tá bom. Eu achei que a gente ia terminar depois do meio-dia. Então tá legal. Mas, Fábio, parabéns, hein? Muito bom trabalho. Eu acho que as respostas às perguntas foram precisas. Então, assim, eu não posso adiantar resultado nenhum, porque eu não participo da banca de deliberação, mas eu acredito que a gente tem grandes chances aí de ter uma aprovação aí.
Ah, legal. Eu achei que os comentários do professor Hamilton foram bem legais, porque eles foram bem orientados a talvez alguns tipos de técnicas e de costumes de designers, né, de design de fabricação mais em nível profissional, dizemos assim.
Uhum.
Isso foi uma coisa bem interessante, uma perspectiva diferente, né?
Mas
e complementar o que eu fui feito.
Mas você sabe que a maneira como você configurou o seu circuito em estágios que habilitam e desabilitam é uma forma de trimming já.
Uhum.
Tá? Quer dizer que se você tivesse alguma variação de processo, você poderia, por exemplo, compensar isso com algum desses estágios, tá?
Entendi.
Mas assim, o trimming ele pode ser aplicado a vários pontos do circuito, né?
Uhum.
Como, por exemplo, se você tivesse algum problema de adaptação de impedância, você poderia ter capacitores ali que você só acionaria se você tivesse algum desvio, né?
Uhum.
Mas é algo que a gente realmente usa muito quando os circuitos são circuitos finais, né? Porque a variação de processo ela ocorre e fazendo um trimming você consegue trazer de volta o seu circuito para aquela configuração inicial que você fez nas suas simulações. Aquela é a boa configuração. Uma pequena variação pode ocorrer na fabricação, você traz de volta para aquela configuração que é a melhor otimizada e o circuito vai funcionar igual normalmente.
Entendi.
Tá? Entendi. Infelizmente, às vezes no doutorado a gente não tem tempo de pensar em trimming, a gente está pensando em tanta coisa que não dá tempo de pensar em trimming. Mas se fosse um produto, de fato, com certeza a gente teria alguns pontos críticos que seriam observados e a gente teria previsto possibilidades de correção via trimming, né? A gente vê isso naquelas simulações corners que você fez, né? Você acaba identificando quais são os pontos que são mais críticos e para esses pontos mais críticos a gente acaba fazendo essa redundância para ter certeza que o circuito vai funcionar.
Curioso. Muito legal, muito legal. Talvez pelo fato também de uma equipe ser maior na hora de desenvolver esse tipo de circuito e tal, acho que a quantidade de olhos e atenção e de variáveis do circuito, elas conseguem ser melhor contornadas, né, ou melhor preparadas, enfim.
Exatamente. Em uma equipe de design, de fato, você estaria com vários outros colegas trabalhando nesse circuito, né, então você teria a sua função e teriam outros colegas responsáveis, inclusive, por pensar nos trimmings e tudo mais, né. Numa tese de doutorado, basicamente o teu circuito é seu, né, é o seu bebê, né. Então, enfim, você cuida do seu bebê sozinho quando ele chora, quando ele precisa ser alimentado, não é verdade? Então a gente não tem tempo de ver tudo, Fávero, mas isso é normal, tá? Se você tivesse numa equipe de projeto, fazendo um PA para um produto, você teria tempo para se preocupar com essas coisas, porque vários outros periféricos do seu circuito, outros designers estariam fazendo, e aí o tempo é otimizado, tá? Então, não se preocupe, é normal. E alguns doutorandos acabam tendo esse tempo, talvez até por trabalhar full time no projeto, não é o seu caso, né? Você tem o seu emprego e a sua tese, né? Então você divide o seu tempo entre o seu ganha-pão e a sua contribuição para a ciência, né? Então é normal que você não tenha tempo de fazer tudo, viu? Mas, assim, provavelmente se a gente fosse fabricar esse circuito, em alguns pontos a gente colocaria trimming sim, como a gente fez em outros circuitos, até no circuito anterior que você fabricou a gente previu isso, né? Mas enfim, isso não tem demérito nenhum.
Legal, legal.
Fique tranquilo. O Bernardo vai ficar nas duas salas, pelo que eu tô vendo, ele tá aqui, mas tá na outra. Eu queria agradecer também, aproveitar a oportunidade para agradecer o Eduardo, que está fazendo o broadcast pra gente aí. Obrigado, Eduardo. Eduardo é nosso parceiro aí, sempre nos broadcasts das teses do GIX, ele está aí com a gente. Bom, Fábio, deixa eu ver se alguém falou alguma coisa para você aqui no chat. Nós temos aqui a nossa secretária Maria Inês, que lhe parabeniza, parabéns, doutor Fávero, mandou até um aplausozinho.
Obrigado.
Renato Carvalho, congrats, Fávero, nice work. Bruno Tarui, parabéns, Fávero. A Poliana também está aqui, mandou um parabéns para você.
Obrigado.
Jonathan Teixeira, parabéns, chefe.
O Jonathan é estagiário lá, nosso.
Maravilha. E Emerson Silva, parabéns pelo trabalho e apresentação.
Legal, muito bom. Muito obrigado, pessoal. Muito obrigado por estarem juntos e por estarem aqui escutando um pouquinho do que eu fiz. Muito obrigado pelo companheirismo.
Muito bom, muito bom. E a vantagem é que agora a gente deixa depois a sua defesa gravada no nosso canal do YouTube, né, Fábio? Então, aqueles que por alguma razão não puderam estar aqui nesse horário, eles têm a oportunidade de assistir depois, né? Então, compartilhe com seus familiares, com seus amigos, com seus colegas de empresa, né, enfim, com todas aquelas pessoas que você acha que vão se interessar por isso, é sempre bom. A gente está deixando gravado na história aqui a sua defesa. Uma das vantagens que a pandemia trouxe para a gente, né, a gente poder gravar a defesa e deixar aqui para que outras pessoas possam assistir, o que a gente não podia fazer antes, quando era presencial, a gente, não que não podia, a gente não gravava, né, poder, acho que a gente até pode colocar uma câmera na sala e gravar, mas a gente não fazia isso, então isso é uma das vantagens aí que a gente tem, uma das pouquíssimas vantagens da pandemia, vamos dizer assim.
Isso é verdade.
Então,
eu achei que também com a apresentação, assim, com a apresentação remota, eu percebi que eu estava um pouco mais tranquilo do que eu estava em relação com a minha defesa de mestrado, que foi presencial, né? Então eu lembro que eu estava muito mais nervoso. Eu não sei se é por causa da preparação, né, de todos esses anos trabalhando nesse assunto, mas eu acho que o fato de ter sido também remoto facilita um pouco, porque eu consigo focar nos slides e lembrar do que tem que falar e como falar e tal. Acho que isso também é legal.
Eu acho que, acima de tudo, é a experiência, Fábio. Você hoje é uma pessoa muito mais experiente do que aquele engenheiro que defendia o mestrado, entendeu? Para se tornar mestre, né? Você hoje já é mestre, você trabalhou durante muito tempo com esse assunto, você tem muito mais experiência, tanto de vida quanto profissional, e isso é uma das coisas que facilita também. Claro, tá em casa, sem estar precisando olhar no olho das pessoas, também às vezes não desvia a atenção, né? Quando você olha no olho das pessoas, eles desviam um pouco a atenção e tal, mas, assim, provavelmente seja a sua experiência, sim, né? Então você está pronto, isso prova que você está pronto para receber esse grau a mais aí.
Muito bom, muito bom.
Enfim, todas as especulações, não sei se eles vão te aprovar, tá? Tô aqui,
Pois é,
enfim.
speculations.
Estão voltando aí. Ah, não, foi você que tirou a apresentação.
Ué, Nossa, aqui também mudou.
Eu voltei, vamos esperar os outros membros. Assim que eu should device deck.
Beleza, tranquilo. Eu fiquei fazendo meio de campo aqui, Bernardo, para não ficar um silêncio absoluto.
Obrigado.
Tranquilo.
Fávero, se você quiser, inclusive, né, ligar essa câmera.
A minha câmera está ativa.
Por algum motivo, para mim, não está aparecendo, mas olha.
Para mim, é tua que não está aparecendo. Por algum motivo.
Eu estou vendo o Fávero que sim, tá, Bernardo? Tá ligado a câmera dele.
Ok, não. Acho que eu tenho que fechar outra. So, Fávero, we have come to a decision. So, all of the committee has decided to approve you in your defense here for your PhD.
Congratulations.
Congratulations for that, Fávero.
Thank you so much.
Of course, to have your degree, you have to deliver us a final version of your thesis that you have to incorporate the corrections that they have decided. But in this very important phase that is your defense, you have been approved. So if you would like to address all of us who are watching, please feel free to say whatever you would like, and congratulations again for your work, for your approval here today.
I would like to thank you all. Thank you, Professor Henrique, Professor Hamilton, Professor Lima, Professor Pichorin. Thank you, Professor Bernardo. Bernardo was a really, apart from being my advisor, he was a really great partner to work with. Thank you for advising me and giving me ideas and suggestions and paths in my work. Also, I would like to thank Professor André Mariano, who 6 or 7 years ago believed in me and gave me an opportunity to do my master's at the Federal University of Paraná. I feel really thankful for all your insights. I know you all have provided me with all great insights and visions and suggestions for my work. It was really nice. Thank you so much. Thank you.
Congratulations.
And I would like to suggest Bernardo, turn on the camera and you put the first slide to the presentation to take a picture of, since we are not together physically, at least take a picture of the screen.
It's a good idea.
to have
Yeah.
Yes, actually, my camera was on here, but I could not see yours. I don't know why. Let's see if I will appear now.
Okay.
No, I'm not there. No, I'm not there. Just give me a minute. I will leave and re-enter the room.
Oh, we see you. Now we see you. We don't listen you.
Yeah, you're much.
But we see you.
Okay, now
Okay, now we listen to you.
Congratulations, Fávero.
Thank you
Parabéns.
so much.
Congratulations.
Let me take some screenshots of you.
Yes.
Yeah. Okay. Thank you so much. Thank you so much. Let me see if
Thank
it's.
you.
Oh,
Nice to see you all again.
Oh, you
Nice to
too.
see you.
yeah, great. I'll share with you guys the photograph.
Thank you. So here we conclude this session, this PhD defense. I thank you once more everyone who followed, everyone who participated, and once more I congratulate you, Fávero, for your achievement. Thank you everyone, and see you some next time. Thank you.
Thank you so
Okay.
much.
Okay.
Bye bye.
Thank you, my
Bye,
friend.
guys.
See you.
Bye.
See you. Bye bye.
Bye.
Bye,
Congratulations.
Mariana. Bye,
Bye-bye.
Eduardo.
Thank you.
Bernardo.
Obrigado, pessoal. Obrigado. Tchau, tchau.
Bye, everyone. Thank you.
Okay.